Today let's discuss the physics of heat. We're gonna divide this chapter into three sections, trying to answer three questions regarding three concepts that are interesting. Each one of those has associated a law, and altogether we're gonna make three of the four fundamental laws of thermodynamics. The idea that everything we're gonna do during this chapter is going to be based on two perspectives. One perspective is gonna be macroscopic, and the other one is gonna be microscopic. So far we've been saying that solids and liquids, or solids and fluids, excuse me, are just two different types or two different states of matters, but that ultimately everything boils down to how the particles are interacting with each other and how they are just arranged in the material, right? We had the distribution or the classical division on solid, liquid, and gas based on the questions of how does it change its volume or how does it change its shape when transferred from one container to another. In this chapter, we're going to see towards the end of this video what is this ultimate reason, which is what we call the kinetic theory of gases. Now, there's three concepts that we're going to treat today. One is going to be temperature, the next one on the next video is going to be heat, and finally the last one is going to be entropy. These three are the three fundamental things that we need to understand, although we may say like actually Boltzmann parameter is actually the one Boltzmann parameter is the one that it's relevant, not temperature, but those things are beyond the scope of physics 2053. So we're going to just use that. And those are going to be referred to phenomena that we observe. Some things are hot and some things are not. And some things that are not hot become hot. For instance, if you park your car outdoors, it becomes hot, right? And so these are things that we observe and we want to be able to describe them. And historically, first of all, we're going to be describing them from a macroscopic perspective, right? It's just fundamentally we observe something. We're going to be in the macroscopic world, in the real world, let's say, or in our day-to-day life world. And then we want to describe that from physics. Then we're going to see that that behavior is actually or ultimately described as the result of the microscopic behavior. To the macroscopic behavior, we could probably do a chart to see this. To the macroscopic behavior, we're going to answer these questions from the point of view of thermodynamics. This is historically the first one to be developed because, of course, people didn't know about or didn't have evidence or the math to describe the macroscopic behavior. But they were still, of course, being able to characterize and to study heat and hotness and all those things. And the other one, of course, was going to be the micro. And the micro behavior is typically described by statistical mechanics or statistical physics, which is going to be, of course, applying statistics to ensembles of particles and saying that the macroscopic behavior is just the result of taking an ensemble of particles and putting it. So if we make a diagram, let's say this is a solid object, this one on the microscopic level, we're just going to say that we have many of the particles together, and this together is what actually makes that object, right? So this is the relationship we're just trying to say. At the microscopic level, we're going to be describing with statistical mechanics. At the macroscopic level, we're discussing with thermodynamics. And there's three questions that we're trying to answer, right? And then it's going to be given, or three questions that we're asking is what is hotness? Then we're going to ask how something becomes hot, or how hotness works. We could say not in the molecular level, which is going to be answered here, but rather how something becomes hot, right? So if I put one object next to another, why does the ice melt and become water, or why does water boil, or things like that, right? So how does things like that work? So these are the three things that we're going to try to answer. And the third one, is going to be why this happens. Because there's one observation that we make, which is that things that are hot become cooler when they are in contact with something that is cool. So something cool becomes hot and something hot becomes cool. And that when you put them in contact, right, for the thermal equilibrium. And so there seems to be certain directionality, on the transfer of heat, as we will discuss this. To the question of what hotness is, of course, the answer is going to be temperature. We're going to define temperature precisely as that, as the hotness of something. How hotness works is going to be described by heat. And finally, why it works the way it does is going to be answered by entropy. And so we're going to have entropy described as S, heat as Q, and capital T for temperature. And we're going to have the zeroth principle of the zeroth law of thermodynamics for thermal equilibrium, which is going to be the law in thermodynamics for temperature. We're going to have the first law of thermodynamics, which is conservation of energy for heat, and we're going to have finally the second law of thermodynamics for entropy, that it's the arrow of time, or it's the directionality of heat transfer, and it's going to be a set of discussions. Every one of these is going to have, every one of these concepts is going to also have or find application. In the case of temperature, we're going to see thermal expansion as the application of everything. It's going to be just thermal expansion. We're going to see how things expand. In the case of heat, we're going to have what we say heat transfer is going to produce what we're going to describe finally as a specific and latent heat, right? This is going to tell us how things increase their temperature, but also how things change phase. And finally, from the point of view of entropy, we're going to approach this from the applications of heat engines. In general, engines or heat engines, whether they're working as heat engines themselves, or whether they're working as refrigeration systems or heat pumps, which is basically the same but from a different perspective. And this is going to be the entire discussion now. Now we're going to start discussing temperature, what hotness is. We will see also the zero law of thermodynamics, which talks about thermal equilibrium, which is the one that allows us actually to make this distinction. And finally, let's see the effects of thermal expansion. This is what we're going to discuss today. The other things, we will discuss them in a later video. So let's start first with the idea of temperature. So temperature is just a way of characterizing how hot something is. Again, and that this is the traditional definition, is how hot it is. If you go to the dictionary, you're probably going to find that. By now, you of course know that temperature is actually a measurement of how fast the particles are moving, or the kinetic energy of the particles inside the gas. But that's going to be a conclusion that comes centuries, of course, after we introduce the idea of temperature, because everyone understands that some things are hot and some things are cold, and you touch the stove and it's hot, or you touch an ice cube and that's cold. And so we know also that the same thing can be hot and cold, because the car parked on the garage is okay, but if you park it under the sun, it's super hot. If you park it on winter outdoors, it's going to be cold. So the same object in different environments is going to behave differently. And so we have there are properties of how temperature works that are related to the material, but there are other properties that are related to the environment. But the first thing that we're going to do is define temperature as how hot something is. And the next thing that we need to know is to see how we can define mathematically this, so we can describe our observations of the outer world in terms of this math, because once we have such a description, then we can use math to see what are the logical conclusions of that, make predictions, and if our predictions match the observations, then we have scientific theory. So how to describe how hot or how cold something is? You probably can just say, oh, okay, I can feel it. And the problem, of course, in feeling, as in anything, is that it's subjective, because it's our perception, our senses deceive us. So if I put my hand, let's say, in a bucket of cold water, and this is cold, and I have another bucket with hot water, and I just put my hand in here, and let's say I put another hand in here, and obviously the arms are not connected, it's a normal human being, and then you just settle them for a while, and then after a while you put your left hand into warm water, let's say, or lukewarm water, you're going to feel that the cold hand says, oh, this is hot. But if you take the hot hand and put it in here, you're going to say, oh, this is cold. But this is the same hotness or coldness because it's the same water. So using senses is a little bit difficult. How can we then define temperature? How we can interact with this idea? How we can observe that? One of the first realizations is that temperature, we do not really observe temperature, we only observe the effects of temperature. And one of the things that is well known is that things typically, when they got hot, they expand, and when they get cold, they contract. We'll see that with more detail in a second. So one thing we can try to do is just say, oh, what if I use a proxy, so to speak? What if I have an instrument that gives me those readings of how hot or cold is something, but in terms of the change that a temperature difference makes on that object? And this is basically the idea of a thermometer. So one of the realizations, which is historically not exactly how it was done, but let's take the classical mercury thermometer, right? Mercury thermometer, you have a column with some mercury, and then you realize that if you have the mercury, you put it on cold water, then let's put it here. What happens with the mercury? If you put it on on cold water, the mercury contracts. And if you put it in hot water, what you observe is that the mercury, on the contrary, expands, right? This is cold water, and let's say this is hot water, right? So then I have now an objective way to characterize how hot or cold is something by means of describing how tall is the column of mercury in contact with that. And of course I could use mercury, I could use alcohol, I could use anything else. And so this is the first way to measure temperatures and to define temperatures. We define temperatures as hotness or coldness or something. Let's define it just as hotness, because later on we're going to see that coldness is just the absence of hotness, right? So we can just define coldness as the absence of hotness, and then just say hotness is what we're trying to measure, and hotness we're going to measure with some proxy, which is going to be a thermometer. So this is the thermometer. The thermometer prevents us from making measurements that rely on our senses, that deceive us. Now we also actually see a height of a column of mercury. If I take it out and I wait and I put it in atmosphere, it goes back. If I put it in, it goes back, and it goes back to the same height, which is of course very important. So this is reproducible, this is a good way of measuring. But here comes the second problem. Let's say that you come up with a thermometer, you build your own thermometer, you're so happy, you took a column of mercury, you put it in there, it worked well, and happy day. And then you call your friends and you tell them, you have two friends that you want to call, ask them to come and play with you with the thermometers and everything, right? And then we're gonna see, let's say that your friend, one of your friends, doesn't have mercury at home. It has the column, the glass column, but has maybe alcohol. And it says, I'm going to use alcohol. I'm going to maybe put some tint in there to make it more visual, and I'm going to bring it. So one of your friends takes alcohol, and the other friend has mercury, but let's say the guy doesn't have the column. And so he says, oh, I don't have this, but maybe he has some centrifuge tube, right? So let's say then that your friend comes with your three friends come, and then you pour a glass of hot water, right? And you put your mercury thing, and it just reaches all the way up to here. But your friend who made this maybe with alcohol, let's say, and the alcohol, I don't know, let's say just the alcohol goes here. And then the third friend that maybe did let's say alcohol. And third friend comes here and does the same thing, but now he doesn't have a column of mercury, then he has mercury, but he has, let's say, a centrifuge tube. And so the centrifuge tube is larger. So let's maybe make something like this to be more obvious, right? And so you observe that the mercury maybe stays there. So this is mercury and this is mercury, but the thing that we observe is each one of you have a different height. So the proxy we're using, which is the thermometer, was just to say how hot or cold is something, which is temperature, is going to be the height of the column. But if you use mercury, it reaches this height. If you use alcohol, it reaches a different height. And more importantly, if you actually use the mercury, but use a different geometry of the thermometer, your column, of course, is going to change. So now the problem is, if you want to report to someone your measurements, you are going to report them in terms of the height of a column of mercury. If you want to measure the temperature of something, you're going to report the height. But now you don't only have to report the height, you also have to report what type of liquid you have, and also you have to report what is the geometry, the exact geometry of your device. And if you send this to someone who doesn't have that liquid or doesn't have that precise material to build this precise thing, then he cannot really make measurements and you cannot talk to each other. So of course you have arbitrary measurements. We define temperature as the height of a column of mercury or the height of a column of alcohol in this particular geometry and so forth. And obviously we're saying that we have a problem here because we cannot understand each other, and this is the idea of units, and this is the idea in particular for temperature of the existence of scales of temperature. How do we solve this? Let's find reference points. We need a standard on which compare every of the measurements. And traditionally there have been two main standards that have been applied across the world. The first one, of course, the most common is that of Anders Celsius, which was a Swedish astronomer and physicist. He realized that his measurement, or the height of the column, is the same in water for a given thermometer, again, of course, when the water is in the freezing point, right? And then he called that 0 Celsius. And then he took another measurement from another reference point, which was when water reaches a boiling point, and that's 100 Celsius. So Celsius needs uses two reference points. One is going to be freezing water, and the other one is going to be boiling water, right? And this we're going to call 100, and then he calls this 0. And anything in between divided in 100 steps. So whenever you go to measure a temperature in between, you're going to have a number between 0 and 100 in Celsius. And that's a good way, because if you fabricate your thermometer, you can go to freezing water and make a mark, go to boiling water, make a mark, and then everything in between divided in 100 steps, and your thermometer now is calibrated to make measurements in Celsius. There's an alternative to this, of course, which is Fahrenheit. Fahrenheit uses two different reference points. The first reference point is going to be, it was a human temperature, or a healthy human individual, which is, I think, about 96 Fahrenheit, and then he used the coldest temperatures that he had available, which was a brine mixture of water, salt, and ice. And so about this minus 20 Celsius, which is what we call 0 Fahrenheit. So then what you observe is that if you transfer this, or you convert, this in Celsius to Fahrenheit, freezing point in Fahrenheit, is 32 Fahrenheit. The boiling point in Celsius is about 212. And so the difference in Celsius from 0 to 100 is 100 degrees, but the difference in Fahrenheit is 180 degrees. So when in Celsius there's 100, in Fahrenheit there's 180, which means that there's a 5/9 ratio when you want to convert from Fahrenheit to Celsius. So those are going to be giving you the reason why you have to multiply 5 times 9 times the temperature minus 32. So you take a Fahrenheit temperature, you subtract, and then you finally obtain the temperature in the other unit. But just be aware with the conversion factors in there. That's not relevant. What's relevant here is that we have solved the problem. We had a feeling, which is how hot something is. We put a thermometer and we observe the effects of the temperature, which is the height of a column. And because every column is going to behave differently, then we come up with the standards. And then we have Celsius standard, and we're also going to have Fahrenheit standard. Later on, with the development of the kinetic theory, we're going to see that there is a third standard which doesn't really require standards, which is absolute, because it refers to a physical property, which is the physical interpretation of temperature. We can advance already that if temperature, we're going to eventually see that it is the motion of the particles, the lowest temperature possible is going to be 0, no motion of particles. Now, quantum mechanics obviously says this is not possible, and the third law of thermodynamics, is going to tell us that it's impossible to reach 0 Kelvin in a finite amount of steps. Those things, we'll see them later. But basically the idea here is there is nothing that prevents us in our observation. There's nothing in here which relies on the microscopic components of nature. All of things are macroscopic observations. So when we come forward with the microscopic, then we're going to make more sense. Now let's see then how we observe effects on solids, how we observe effects in liquids, and how we observe effects on gases. So the effects on temperature on the objects, whether they're solids, liquids, or gases, is basically that they typically expand, although they can also contract. Thermal expansion refers precisely to that phenomena. Thermal, which comes from the Greek therme for heat, and then expansion, just self-explanatory. We saw in previous chapter, in the case of solids, which is where we're going to start, that objects can be stretched, right, or can be compressed by applying forces, right, and the forces produce strains, and the strains then give rise to stresses internal to the system as a result of that external force, which is very important. Now we're going to see that objects also expand or contract in response to external stimulus, which are thermal stimulus, which is basically changes in temperature. These things that we present here are also observational things. The same way that Hooke said, oh, you have an elastic law, right, which was minus k times delta x, right? The restorative force is the result of bringing it out of the equilibrium position, and there's a restorative force, right? And we're going to be saying now that and this was observational, right? So we're going to do the same thing for solids. Let's say that you have a bar of metal, right? It has a given length that we can call L sub 0, and then you raise the temperature at T sub 0, and then you raise the temperature, let's make it here then, right? With a T larger than T sub 0, what we observe is that we have now a new length which is larger than L sub 0. So what we can do from here, what we can do in here is just observe that there is a change in length as a result of the change in temperature. And of course there is proportionality between the change in length and the temperature. So if you repeat this experiment, let's say you increase 5 degrees, then you increase 10 degrees and measure, 15 degrees and measure, 20 degrees and measure, what you're going to end up observing is that for a given bar, you're going to observe a relationship of this time. The change in length is going to be proportional to the temperature. Let's say you measure at these temperatures. But what you observe is that you have sort of a linear behavior. In the first approximation, this is the case. The same thing here. If you go crazy, you get out of the range. In here, if we go to the transition temperatures or we go to very extreme temperatures, we're also going to have troubles, right? So we're going to have to keep always within range that makes sense. So within a given range of temperature, the objects deform in their length. They have linear, it's linear. So we call this linear because it's a line, right? So and what that means mathematically is that what you're going to observe is that mathematically that's proportional to the length original of the object, the temperature change, and alpha, where alpha is the coefficient of linear expansion. Okay, So this is purely mathematical. We can obtain this alpha for different materials. Why for different materials? Because each material is going to have a different expansion coefficient. Different materials behave differently in response to the same stimulus of temperature. Even if you have a bar, one of wood, one aluminum, one iron, one steel, and you subject them to the same change in temperature, the change in length, even though they're the same length and the same change in temperature, the final change in length is going to be different because it depends on alpha, which depends on the material. Now, how can we picture this? And again, we haven't used the atomic theory, but how we can picture why this thing happens, why physically the objects expand. This is maybe a good way of seeing it. In solids, we have the atoms, let's say, bound together. Let's say the bar is just made out of a chain of particles. Each one of these particles is vibrating in the neighborhood, so it's shaking back and forth, let's say, in that. So if I want to say what is the length of this object, well, all the chain of atoms, and of course I'm assuming it's a single chain of atoms, but that's ridiculous, but they're just vibrating in place. What happens as I increase the temperature? Remember, temperature is going to be, and we will prove it, temperature is going to be, or we will show why. Temperature is going to be a measurement of the of the motion of the particles, right? And so when you add heat, the particles are going to start moving more and more. So we're going to end up finding is that the particles now are going to start moving larger distance. They're going to start vibrating in the case of the solid, much larger. So now the effective size is going to be this one. So because the particles here were moving a little bit and here they're moving more, effectively the length changes. So as you increase the temperature, this will be T and this will be T larger than T sub 0, right? As you increase the temperature, the atoms start to vibrating larger or more, or the amplitude of the vibration rather, it's larger, and so the effective length of the bar, which is made out of all those atoms vibrating, then becomes larger. Now there's an effect of or a consequence of this. If I have a bar and I put the difference in temperature, the bar expands. There's no external force in here. Because there's no external force in here, there's no stress in here, right? The bar is just expanding. Now, what happens, however, if a bar that was supposed to expand, is limited because it's, let's say, compressed by two columns. Imagine, for instance, a beam which is built onto, this is a wall, and so here you have a steel beam, and then you have it fixed at the edges. And now this was a T sub 0, and I go from T sub 0 to T. In other words, I have a change in temperature. Because I have a change in temperature, they're going to have a change in length. But this thing cannot move, cannot go there anymore. It cannot expand. So why doesn't it change even though it's trying to expand? Because there is an external force that's applying contrary to this. And that force is going to produce a stress. That stress, we're going to say, is thermal, that stress is going to be thermal stress, sigma for thermal stress, and it's going to be proportional. Remember that we said before that the stress, for instance, normal stress was proportional to Young's modulus times strain, right? Where stress is defined as the normal force over the area, and the strain was defined as the change in length over the original length. Now I can rewrite the force is going to be such that this length doesn't happen. So what I can rewrite this is just to observe that I'm going to have Young's modulus still, but now I'm going to have thermal stress. And how much is the thermal strain? How much is the thermal strain is the change of length over the original length. So that's delta L over L sub 0, right? So that's going to be delta L over L sub 0. But delta L over L sub 0 is alpha times delta T. So what I observe is Young's modulus alpha delta T. So what happens when you try to, let's try to make this clean. What happens when you raise the temperature in an object clamped at both ends, hold in position? Well, because of the heat it tries to expand, but that's prevented because there's an external force pushing it in. And that external force, which gives rise to a stress, which is going to be proportional to Young's modulus, which is elasticity, proportional to the coefficient of linear expansion, how much is expanding a material, and proportional, of course, to the change in temperature. And here's the thing. Because if the object is increasing the temperature, the object is trying to expand, there's a force that opposes that. If the force is opposing that, there is now a stress, and that's the thermal stress. That wouldn't occur if there was nothing opposing it, because this is not the result of an external force pulling, as before we saw in chapter 6. This is the result of actually, this is the opposite. This is a force impeding that expansion, right? So this is natural. This is just the atoms just relocating, so to speak. But now we have a force that is preventing that, and so we have stress. That thermal stress can go above the maximum compression or tensile stress that the material can hold. And if that happens, the material breaks, because we leave that elastic regime that we were talking about in chapter 6. So now we see why it's dangerous that objects that are subject to large gradients in temperature, large changes in temperature, you have to, when you're doing a structural design, you have to account for these things. Because, for instance, if you make an object that expands a lot in summer and contracts a lot in winter, then if you have, let's say, tracks of a train, those are made out of steel. The tracks are, of course, fixed because you don't want tracks moving around. As they try to move, they just start to distort. And so you can end up seeing that this is a nonlinear effect. The result of the track, if this was a track, the train would go like from here. So the result of the thing trying to expand is eventually just deforms, because if it was ideal, this wouldn't happen, but there's nothing ideal in the real world, right? So any imperfection is going to create a weakness, and the material is going to deform, and it's going to deform out of place. And this is an important problem, and this is why you see also in the roads, for instance, there's some gaps in bridges and things like that, because engineers are accounting of how much is the temperature change that we're going to observe in this location during the year, winter versus summer. Well, let's account for the material, how much is going to expand, let's leave some room, and let's see. But you also see that, for instance, in summer and winter, when if you have, for instance, a door of wood or a window, sometimes the window doesn't close well. There's other effects also like humidity, blah, 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 but basically this is also related to these expanding and contracting elements. And this is also the reason why if you have some screw, for instance, or ball seized in your car, you can obviously use lubricant oil, but you can also take a torch and heat it and cool it down, and that thermal stress is capable of breaking the rust and you being able to unbolt it. This is thermal stress. We're going to see some examples of this. But this is just basically an application which is a consequence of the law of this equation, which is not a law, it's just simply an observational thing. We observe that objects change their length when they change their temperature. Now, how do they change their length is proportional to alpha. And here a note of caution is typically materials have a constant alpha within a given range, but if you go with a material that doesn't have constant alpha in a given range, then you cannot use this, or you have other problems that you have to account for. The other thing is that typically you assume the coefficient is positive, which means if I increase this, this is positive, this is positive, this is positive, this is positive. So objects expand. But some objects do have an alpha which is negative. If the alpha is negative, if the coefficient of expansion is negative, an increase in temperature, this is positive, and this is negative. Therefore, the product of all of this is going to be negative. Delta L is going to be negative. That means that it contracts. Some objects contract as the result of a temperature increase. And so you think about, for instance, some rubbers and some plastics. For instance, the ones you use to protect wires when you're soldering them, you put heat and they contract and they just embrace the wires. Well, those are negative coefficient of expansion coefficient. And then you can even think of expansion coefficients that are zero. Again, within a range, everything is within a range. And that range of temperatures, if expansion coefficient is zero, means that the object doesn't change. And that's very important when you're designing. There's some ceramics and some compounds and some micro and nanostructuring that you can do to actually have structures that effectively have that sort of material properties. That's the field of material properties and nanotechnology and engineering at the nanoscale and microscale. So that's the idea. And here we can make composites, and we can structurally achieve those effects with ceramics and other metamaterials, sometimes are called, because they are materials with properties not found in nature. So we can achieve those effects, and that's very important if I want to have, for instance, applications where I need very high precision in optical interferometry I'm thinking about, for instance, or if you're trying to do aerospatial applications where you're going to know, oh, if the sun is hitting, this is super warm, if the sun is not hitting, this is going to be super cold. So you have like a huge gradient, right? Like being on the desert, right? There's no mild temperatures, like huge gradients, huge differences. Then you have to be very careful with these things, because typically we design things to be applied in a specific range. If we go out, good luck, right? So this is in terms of solids. Typically solids expand. Now, solids expand in one dimension whenever they have one dimension which is larger than the other ones. In the case of a bar, the length of the bar is much larger than the thickness and the width. Both thickness and width are going to be described by the same law, or by the same equation. So they both going to increase with the temperature, because that's only given by this. But the ratio of the change to the original length, because the length is very little, or let's say the change is going to be proportional to the length, because the length of the width and the length of the dimensions of the width and thickness are very small, you can pretty much disregard those and just focus on the ones of the longer dimension, which is many times what we're interested in. For instance, in the case, we don't really care that much of how much this expands sideways, usually, right? But we certainly care of how much it's trying to expand in the longer dimension. So this is with respect to solids, let's see with respect to liquids. So the case of fluids, we typically describe differently, because there's no defining a length in a fluid, in a liquid, it's pretty meaningless, right? The liquids take the shape of the container and they're incompressible. Solids are incompressible and they keep their shape, and gases are compressible and they keep the shape of the container. So gases and liquids are fluids. We said solids are solids. So the idea with liquids is defining a length change is difficult. Then we have to define how, instead of a length change, we define a volume change. And in the case of liquids, and also by the way, solids, that doesn't change. We have what we call volumetric or volume expansion. And basically this is the same way as before. We had a linear expansion. This is going to be also linear anyways, but in terms of volume at least. We said that the change in length is proportional to original length and delta t. Now for the case of volume, it's going to be pretty much the same. It's going to be the change in volume is going to be proportional to alpha sub v. Now with v we mean this is the volume coefficient of expansion. The original volume and the difference in temperature is the same. And so this is going to be applying also to liquids and gases, to liquids and solids. The problem with gases is that the gases do not have any interaction between the molecules, they're free to move, and so measuring volume is going to require the developing of the ideal gas law. So in change of volume, it's going to be exactly the same thing. We only need to consider that the change in volume is proportional to a constant times v sub 0 times delta t. An interesting thing happens, of course, is in solids that are isotropic, that they don't have a particular preferential direction. We're going to observe the coefficient of expansion for volume is going to be about 3 times that of the linear expansion. Whereas if we were talking about surface, we could even make an equation that goes like, oh, the change in area is proportional to the alpha of for area a sub 0 delta t. So this equation might be more irrelevant, for instance, when you have plates, right? And plates are 2-dimensional things, right? We just don't use this, but anyway, you see the idea. Basically, what you're observing is that the change in whatever dimensions in the area, for instance, is proportional to the original area, is proportional to the temperature. In this case, for those solids, this will be about twice that, right? And a good approximation, most materials behave that way, most solids, behave that way, right? In the case of fluids, liquids, we cannot make these distinctions, we cannot make these interpretations, we just simply use this equation. Liquids expand, and they expand, you can think about in the same way, but also molecules are moving around, so it's a little bit more precise, but basically it's the same idea. You're moving more, you're raising the temperature, you're moving farther away, they occupy a larger volume. And finally, we have the idea of gases. And to construct a gas expansion law, we're going to do it from an observational perspective. There's nothing here fundamental and nothing here fundamental. We can understand with our understanding of atomic theory why does this happen or not. When I say fundamental, I mean in the equation, right? There's nothing fundamental in the equation. We haven't derived this from first principles. This is purely observational. We observe this is linear relationship, we write it down, and it holds well. We observe the volume also changes linear with the temperature, and so we write an equation and we see it actually holds. We're going to do something similar, but now for gases. The problem with gases, again, as we said, is the gases fill the container, and gases then are not, and they're also compressible. So we have to play with different things. We have to play with the volume, but we also have to play, in the temperature, we also have to play with the pressure. And if you remember, we said there's also another thing that matters in terms of gas. Gases are made out of particles, and again, we will put all these ideas together with kinetic theory, which is the idea that the particles, how many particles you have, is going to matter. So there's 4 observations that we're going to make. The first one was done by Boyle, and that's why it's called Robert Boyle, and that's why it's called Boyle's law. What Boyle's doing is just saying, let's say I have a container with a certain, with a certain gas, and I put it in a bath, so I can, obviously this should be fully submerged, but anyway, you get the idea. I can control the temperature in here, and I increase the pressure. For instance, this is a piston, let's say this is a piston, and so you can have, right, and so you can push down, and as you push down the pressure, what happens? That as pressure increases, volume decreases, and as the pressure decreases, volume increases. So this is Boyle's observation. So he says, hey, at constant, we can say constant temperature, we observe that pressure is proportional to the inverse of volume. This is Boyle's law. First observation. Second observation, let's try to put it here. Second observation. Maybe we can use this space over here. Second observation, let's put it in here. Second observation comes from Charles, finally. Second observation comes from Charles. And Charles is saying, well, what happens now is, let's say I have I can keep the pressure constant. So how can you achieve that? You can think of a movable piston, and now it's you pushing down. And you have a gauge or something to ensure that the pressure is always constant. Or for instance, if you have atmosphere, then atmosphere is constant pressure, so the external pressure is always the same. So that's another way, right, to make sure that the pressure applied on the object is it's constant. So you have to think of a way of actually achieving pressure constant. But basically what he's saying is what happens if I have a volume with a gas, and now I increase the temperature. Let's say, for instance, yeah, let me say that, and and then maybe with a movable piston as well. Let's make a movable piston to visualize this one. So, and again, remember we're just trying to keep this constant, and I have a certain volume and certain temperature, and I say, what happens when I increase the temperature? And so Charles says, oh, what happens? That's actually Charles' law. So what happens when you increase the temperature is that the volume, you observe that the volume increases. And when you reduce the temperature, you observe that the volume decreases. You can think of a balloon, inflate the balloon, put it close, and hope that it doesn't burst, and put it close to a flame. The temperature increases, the balloon expands. The temperature decreases, the balloon shrinks. Take a water bottle, empty it, or drink it. It's air now, so it's a gas. Put it on the fridge, and what's going to happen? Temperature drops. What happens to the bottle? Shrinks. It happens also when you have liquid. So you have a half-filled bottle, you can observe that. Put the bottle on the fridge, because you drink, and the air comes in atmospheric pressure, so it's in equilibrium. You close it down, that's atmospheric pressure. You put it inside the fridge, the temperature drops, the volume drops, so the pressure inside drops. Well, we'll see that. Pressure is the constant thing. So we're going to put pressure outside, so the thing is going to shrink. So basically, this is an observation that we have. Volume, then, at constant pressure, what we observe is that temperature is proportional to volume. So this is the second observation that Charles does. There's going to be a third observation by Gay-Lussac, which is going to be Gay-Lussac's law. The observation for Gay-Lussac is going to be that, well, you have seen that we have pressure and volume, temperature constant, we have temperature and volume, pressure constant. Now we're going to have to keep volume constant and do changes in temperature, right? So now we're going to have a gas, and the container is sealed, and it's strongly sealed, right? It's robust, let's say, robust enough. So now I have somehow a way of measuring. Here I have a barometer that measures the pressure. And then what happens when I change the temperature on the gas inside here? When I increase the temperature, what I observe the barometer does, the pressure increases. If I drop the temperature, for instance, I put it in a bath of ice, the temperature drops, and what I observe is that the pressure drops. So the consequence that Gay-Lussac extracts is that the constant volume temperature is proportional to pressure. So that's not bad. We have three observations, but there's a fourth one, and that comes from Avogadro. What does Avogadro says is that, okay, now let's keep temperature and pressure constant. So for instance, inflate a balloon and assume the balloon is in equilibrium. So let's take pressure and pressure constant. So temperature is atmospheric and pressure is, and environmental and pressure is atmospheric. And then you take two balloons. The balloons are identical. You inflate one, let's say 1 second. You blow for 1 second, and then you inflate the balloon. This is for 1 second. And then you inflate another one for 10 seconds. What do you observe if you, instead of 1, you blow for 10 seconds, right? For 10 seconds. What do you observe? You observe the balloon is larger. And so what do you conclude from here? Well, this is larger than this one. Of course, you are not going to say how much I blow. What is the difference between this and this one? Well, the difference is the amount of gas that you've put in. So Avogadro realizes that at constant at constant P and T, if the amount of material, which is another way of saying the amount of molecules in there, increases, volume increases. Let's write it here. When the amount of molecules increases, volume increases. When the amount of molecules is lower, the volume is lower. And that's why if I open this air gas out, then the pressure, the volume, the balloon shrinks, right? So I'm taking material out. Vacuum again is just removing material. We saw that in chapter 10, so now we're going to see this thing. And so, of course, the thing is that the volume is proportional to the n. So let's recap all these 4 observations together. Let's put them here, let's erase and put them here and see what is the conclusion of this. So now we have all the 4 laws, and this is Boyle's law saying that pressure is inversely proportional to the volume at constant temperature. The volume is proportional to temperature at constant pressure. That pressure is proportional to the temperature at constant volume, and the volume is proportional to the number of molecules at, and this is of course for gases, right? At constant temperature and pressure. You can play with these things and see, can I find an equation that fulfills all the 4 conditions, remembering always the constant conditions? Well, you can find that this pressure times volume is proportional to the number of molecules times temperature. And if you have a way of measuring pressure, which for instance we know how to do with a barometer, and you had a way of measuring volume, for instance a ruler, just calculate the volume, and temperature, because we just introduced thermometers, then we can find that the product of P and V is going to be proportional to temperature. That proportionality is going to be something times the number of moles. So is there any way of, number of molecules. Is there any way of, this is number of molecules, right? This is number of molecules. So is there any way to characterize that? Well, you know from chemistry, of course, that the number of molecules, or rather the number of moles, it's equal to the mass divided by the molecular weight. Why? Because if I have 10 kilograms and each one of the molecules is 1 kilogram, right? Well, that will be the weight of the molecule, that's the mass of the molecule, that's going to give you the number of moles. But how many molecules are actually, inside in there? Then that's given by the ratio of the number of molecules to the Avogadro number. So if I actually want to have, how many moles something has, I divide by the molecular weight, and if I multiply times the Avogadro number, then I have the number of molecules. So first thing I can do in here is I can see that then I can write this. In fact, there is a proportionality. Somehow I had a way of calculating that. We could just rewrite it. N is going to be Na times N, and then N it's going to be Na times M over MW, right? And so you would have that, the way of describing N in terms of those things. What's relevant, however, anyways, is that when you write it in terms of molecular number of molecules, you have an exact relationship, which is given by number of molecules, Boltzmann constant times the temperature. And because this is inconvenient, you probably know it in terms of N. N is Na divided by N, so we can write that Na times Kb times T, and this you recognize is R, which is the constant of universal gases. And you assert that this is now an equality that does not depend on the type of gas that you're using. Neither does this one, by the way. Okay, so these are 2 ways of formulating exactly the same thing, where this constant and this constant is going to be different, but this is number of moles, and this is just R. It's are related to each other, so like this, right? So that's how you go from one to the other. So the constant, Boltzmann constant, is the constant universal constant of gases divided by the Avogadro number. Anyways, we will start here is now if I increase the pressure and I keep volume constant and I keep volume constant, increase pressure, I increase the number of material constant, which in all these experiments we always kept it, although we were not doing it explicitly. As soon as we come with Avogadro, we realize, hey, there's another thing, which is the number of molecules is a constant, because amount of material is constant in all these experiments. So if I increase the pressure, I keep this constant, I keep this constant, this is a constant, so it's constant, then this needs to increase, which is this one. If I increase this one and this is constant, then this needs to reduce, it needs to decrease, which is Boyle. And if I keep this constant and I increase the volume, and this is constant, this needs to increase, and if I increase the volume, and this is constant and this is constant, then this needs to increase, which is Avogadro. So we have the equation of ideal gases, right? This is the equation of ideal gases. And this is a good approximation for gases. For ideal gases, it's exactly true. This goes beyond, let's say, the application in physics. We're just going to be saying, how do we study the expansion in solids, linear expansion? If it's volume, volume for solids and liquids, volume expansion, alpha V, initial volume, change in temperature. What about the change in gases? Well, you have to account for the pressure, you have to account for the volume, you have to account for the amount of material, you have to account for temperature. We're going to be using these things now for developing the kinetic theory of gases and seeing finally that connection that we have between temperature, macroscopic observation, and the microscopic nature, which is the motion of the particles. Just one last thing in here again. All of this comes from observation of macroscopic observation, which means there's nothing in here that requires the atoms to exist at all, right? We have that this is basically going to the lab, making some experiments, and observing that these proportionalities are full. And if I combine all these proportionalities, all this evidence together, I come up with this equation, or this equation, whichever you're more familiar, it's relevant at this point. Basically, the pressure times the volume is going to be equal, exactly equal to a constant times the temperature and the amount of material that you have in there. Let's develop now the kinetic theory of gases briefly and see what's the effect of that. So ideas of atomism can be traced back to the pre-Socratics and the 5th century before Christ in ancient Greece, with Democritus thinking that, or saying that everything is made out of atoms, like the arche, the ultimate composition of nature of reality, was just atoms in motion. And this idea, with the success and prestige of physics, is going to be a bolster into explaining everything in physics in terms of mechanisms, as if nature was just simply a machine where you push one button and this moves a wheel that moves another one, and gears, and the mechanisms that result in something, right? This, of course, is going to be demolished with the advent of quantum mechanics, but the effects that culturally, at the very least, affected on the metaphysical dispute are undeniable. And probably we're still at this time in the status quo followers of those ideas of mechanicism. And so slowly people are going to start to say, well, more and more things are, that we used to say they're qualitative and not quantitative. They're trying to say, well, they can be described as motion of particles, and at that point it becomes quantitative. Galileo himself in El Saggiatore has the idea that tastes and flavors and smells could be actually the result of particles, right? And these ideas are going to be coming up again and again, and with more strength, particularly pushed by the development of ideas in fluids, in vacuum, and in heat. Now, the development of the kinetic theory is actually the work of Maxwell, James Clerk Maxwell. It's going to be the result of many experiments and many observations that preceded him, and obviously it would be impossible without the works of, but we will go to that in a different video, of demonstrating that actually of Joule and Count Ramford, that actually heat is just, heat and energy are basically the same, right? And the link between mechanical work and energy that we'll see in the next video. At the end of the day, anyways, what matters here is that these guys are going to be attempting to describe everything that they have observed macroscopically, because the observations macroscopically do not require any adherence to either any metaphysical presupposition, or for that matter, any material presupposition in terms of what compounds or what makes matter, right? We obviously know now that we take now the position that everything is made out of molecules and atoms, and so how those behave macroscopically determines the macroscopic world. But at that time, all the observations that we've done and many that we will do next in the development of thermodynamics are not based on and are not committed to atomism. But once you take atomism and you make certain assumptions, you can actually derive models mathematically that predict the reality. And at that point, your theory is not simply a theory, it starts to become sort of a law, or it starts to take epistemological status superior to just simply saying this is an idea. Well, this idea turns out that mathematically expressed describes nature, right? So you start to believe, oh, nature maybe is this way. The idea of kinetic theory, again, we're going to develop it for gases. Some of the ideas, anyways, can be qualitatively, at the very least, applied to gases and to solids and liquids, excuse me. But we're going to start by taking a gas. We're going to say there's a container. Let's say the container is of a volume V. So this is a length L. Let's start from here. This is area A, and there is N molecules of the gas. And we're going to make what is typically called ideal gas. So we're going to make an idealization of what a gas is. This requires taking particles to be identical. Take the particles to be separated from each other. This also requires to consider that the only interactions that exist, which is probably one of the most important, number 3, the only interactions are elastic collisions. And why is this important? Well, if the interactions are elastic collisions, excuse me, well, we just saw this briefly, but elastic collisions are those collisions where momentum is conserved. Momentum is always conserved anyways, but also kinetic energy is conserved. So Ke is conserved. Right? So particles are far away, particles are identical, and particles interact only through elastic collisions, so kinetic energy is conserved. Now, of course, whenever we have a situation where one of these assumptions do not hold, then we cannot really use ideal gas or the idealization of this gas, right? But for instance, if we have a high pressure and force the particles to be close together, then this number is not going to hold, and 3 actually either. And that's what happens, for instance, if you make a change of phase. If you go from a gas to a liquid, as you liquefy, the bonds between the particles start to develop. Particles start to interact in more ways than just simply colliding. We're saying all interaction is just a particle hits another, period, nothing else. But if you are actually consider a material, for instance, a solid or liquid, you have to consider there is electrostatic and bonding energies that play a role, right? None of those things matter in here. All energy is purely kinetic energy. We'll see what happens when we try to move to something else. One of the first things we're gonna do now is, based on these presuppositions, we're gonna just see what are the logical consequences of that. Based on these postulates, we're gonna see what follows from them. And we're following that mathematically. Once we see what follows mathematically, then we see, is this what happens in reality, and let's extract some conclusions from that. So let's start also by making realize one thing. And we're gonna just briefly go through that, because the proof goes, the rigor for this proof probably is beyond the scope of physics 2053, but we just want to be focused on the concept more than the math anyways, right? The math is just taking the thoughts forward and rigorously, as rigorously as we can be, of course, given the context. Okay, so the first thing that we can see, for instance, if a particle is moving, as a particle moving in a box, it's a particle moving in 3 dimensions. So the particle, of course, is going to have 3 components of velocity. It's going to have velocity in the x, y, and z components, right? One of the first things we're going to say is we're going to take one of the particles. Every particle is moving with different velocity. But we can define what we can call an average velocity, right? So we can say there's an average velocity. And so we can just call it that with these angular brackets. The first thing we're going to say is, because particles are moving randomly and they're identical and indistinguishable, we can take a particle and say this particle represents the gas. And the gas is going to move with an average velocity, let's say. And so the first thing we can say is that the velocity is going to be then the velocity of the average particle moving in any one of the directions. Okay? Basically. Okay, there's many things again. If you want to be precise, we're going to make a lot of things that would make mathematicians go mad, but it's okay. So this is the first thing. So because velocity is in 3 dimensions, the particle is moving in 3 dimensions, the velocity, average velocity, or the mean velocity, if you want, is going to be given by the mean velocity of the x, mean velocity of y, and mean velocity of z, which is just basically. Now, if I take a particle that represents the average motion, and the particles are moving randomly, it means that there is no preferential direction, that the gas is moving, or the velocity is isotropic, right? Because the gas is isotropic, it's just moving in the same, or inside the gas we have isotropicity, which means every particle is moving with the same randomly in every direction. What follows from that is, of course, that the velocity in the x component needs to be the same as the velocity in y and velocity of z. Why is this so? If there is no preferential direction and I take the box and move it, and move it, and move it, and move it, and I keep my axis fixed, now x becomes y, y becomes z, or whatever, I cannot observe any difference. That's what we mean by that. If I rotate this thing around, it doesn't matter. If I look this way, or that way, I'm going to see exactly the same thing. That's what it's isotropic. And so velocity in all these directions need to be the same. What that means is, if I actually calculate what's the modulus of the velocity, which is of course the sum of the square of x plus the square of y plus the square of z, right? I'm going to say that the average square velocity is going to be the average of x, the average of y, and the average of z. And here's the thing, because velocities are all the same, then I can say that this is the same as 3 times velocity of x squared, because this is the same as vx and this is the same as vx, so I have 3 times vx. Or finally, I can say that vx x squared it's equal to 1/3 of the average squared velocity. This is the first result that we follow, and this follows simply by the fact that I'm taking one particle, let's say, to be moving with the average velocity. Because this is the same idea, for instance, we were discussing average velocity or average for any matter. If I say I have a class with 300 students and each one has a different height, I calculate the average, then I can say that I could posit that there is an ideal student which actually is characterized, is described precisely by the average height of the class. It doesn't necessarily mean that one of the students has that height. There's going to be a distribution. Some going to be higher, some going to be lower. We'll get to that as Maxwell, actually, Boltzmann distribution of velocities, right? But what it means is that if I take one that describes that motion, that's equivalent as having one that is moving with that velocity, or rather that all of them were moving with the average one, right? This is kind of the idea what we're having in here. And this just follows because the particles are moving randomly in every direction with no preferred direction. So this just follows, this is simple. Again, the math is not as important as the concept. We're just deriving things based on things that we do all agree, and so we're going to have a result which is extraordinarily powerful, which we are able to develop ourselves. So this is the first thing that we have extracted, concluded. Let's write it in here, let's erase this and continue with the derivation. So we have the first thing, which is the velocity in the x direction is going to be equal to 1/3 of the average velocity. Speed of the average speed. Let's take now a single particle. Let's observe the wall, and let's say the particle is coming to hit the wall. We expect the particle is going to hit the wall and bounce back, and it's going to leave. And let's take only, by the way, let's just take only the x component, right? So we have the particle is moving with the x component, Vx, negative because it's going negative. It's going to hit the wall and it's going to go positive. And I ask myself, well, what is happening here? What's happening here is there's a change in momentum, or if you want, there's a change in velocity. So for instance, if I want to say there's a change in momentum, what I'm going to say is that the momentum, which is the mass, times the velocity at the end, which is Vx, minus mass, velocity at the beginning, which is minus Vx. So if I calculate the change in momentum, what I'm going to find is that the change in momentum is twice the mass velocity of x. Okay? And so, now I say there's a change in momentum, and every time there is a change in momentum, there's an impulse. Change in momentum is equal to impulse, which is equal to the force times the time of interaction. So now I can write that there is a change in momentum, which is 2mvx, which is going to be equal to a force times the time of that interaction. Now, how long does it take for a particle to hit the wall twice? Well, the particle hits, goes there, hits there, and comes back. So how long does it take to do that? Well, it's going to take, if this is the length L, it's going to take the time is going to be given by the distance it covers divided by the velocity it has. So then I can find the time and I can rewrite this in terms of the force, saying that the force is equal to mvx squared divided by length. Now, what is this force? Well, this is the force that the wall does on the particle. So this is actually the force of the wall, because it needs to be an external force. But according to Newton's third law, action-reaction, what the particle does to the wall, or the wall does to the particle does to the wall. So from the point of view of the wall experiences a force which is equal to mv squared divided by L. Okay? But this is a single particle, so we could even call this ice. But how many particles are hitting the wall? Well, all of the sums of all the particles hitting the wall are going to be the sum of all the particles from I1 to I sub n, because we said there's n different molecules. And if each one of those is going to have its own velocity, but this is equivalent of saying that each one of those is going to have its own velocity, but the sum of all of those, I could just say, is going to be the same as the average times n. It's as if I replace each one of those particles with different velocity with a particle characterized by average motion. And in that case, what I'm going to be able to write is I'm going to say that I have the sum of the mass, and now velocity I'm going to say is the square divided by the length. And so the sum from I equal to 1 to n is going to be this plus this plus this plus this n times. In other words, the sum of the force is going to be n times mass Vx squared divided by the length. And because the Vx squared is 1/3 of Vx squared, what I find is this is n divided by L, 1/3 mass Vx squared. Let's rewrite this result again, erase and rewrite. So just let's notice that this is an error. This is not Vx squared. This is just directly Vx. That's why we put the 1/3, right? And so we go back to this result. Now, what is the pressure on the container? We said it's the collision of the particles hitting the wall. So pressure is defined as force divided by an area, the area of the wall. So that's going to be N LA 1/3 M V squared. What's the length times the area. Well, that's the entire volume of the object. So that's actually equal to P, it's equal to n number of molecules divided by the volume, 1/3 of mass V squared. So what do we observe in here is that we can rewrite this as P times V, it's equal to n/3 of mv squared. But what is this? Remember, kinetic energy is 1/2 of mass V squared. So the average kinetic energy is going to be 1/2 of mass V squared. So this is actually twice the kinetic energy. So this is 2n/3 of the kinetic energy average. And the big thing to realize, P times V is proportional to the number of molecules, and it's proportional to the kinetic energy. If you look in here, P times V, or we can just keep the V there, let's say pressure. Let's focus on the molecular origin of pressure. So that means this. So the pressure is proportional to the number of molecules, the pressure is inversely proportional to the volume, and the pressure is proportional to the kinetic energy. What does this mean? Let's bring the V here and say, or rather, what equation do we know for the gases that we just developed? That P times V is equal to n K sub d T. Therefore, P is equal to n divided by V, K sub b T. So what if I write P as the macro? This is macroscopic, eh? This is microscopic, this is macroscopic. So I can just write them together and see that NVKBT it's equal to 2n3V, which we can write as 2/3 of n divided by V Ke. So you already see it. This and this are going to cancel. If I solve for temperature, I observe that temperature is 2/3 of the average kinetic energy divided by Boltzmann constant. Why do we say that temperature is a measurement, is a macroscopic? This is macro. And this is a micro. Why do we say that temperature is a macroscopic measurement of the kinetic energy of the particles? Because of this. Because temperature is indeed 2/3 of the average kinetic energy of the gas divided by kV. This is a constant, this is a constant, this is a constant, this is the kinetic energy. If this raises, it's because kinetic energy is higher. If this is lower, it's because kinetic energy is lower. This is the kinetic theory describing or explaining why temperature is proportional to the kinetic energy of the particles. One last thing from here, we can solve this in terms of V, and if you solve that in terms of V, we can probably write it somewhere. So if we write the temperature is equal to 2/3 of m1/2 mv squared divided by kb, 1/2 and half cancels, so we can solve for v squared, and that's going to be 3t k sub b divided by the mass. And if now we define the root mean square value of the velocity, which is just the square root of v, somehow to characterize the average velocity, we find this. One important thing, this mass is the mass of the molecule, so actually it's going to be the molecular weight. And now we see then the velocity in a gas is going to be proportional to the temperature. We have again the definition of temperature as a measurement of how particles or why particles move faster than others. We have finally bridged with the statistical mechanics from ensembles of particles the macroscopic observations from thermodynamics. The first problem we're going to solve is problem number 1 in discussions, and says there is a still bed of a suspension bridge which is 200 meters long. So let's imagine this is a bridge, and this is 200 meters long, and it is at 200 meters, right? The length is 200 meters, the original length, and then it's at 20 degrees Celsius. So the temperature is 20 degrees Celsius. Then if the extremes of temperature to which it might be exposed are -30, so we want to be working in a range from -30 Celsius to 40 Celsius. So how much will it contract and expand? So basically that's the question. What's going to be the change in length for the solid, in this case being steel, that it's 200 meters long and it's originally at 20 Celsius. Now we know that the expansion of this is going to be given by expansion equations. It says that the original, the change in length is going to be proportional to alpha, which is an expansion coefficient term. We can call alpha sub L if we want to just signal that this is the linear one, so it's just for one dimension, versus the alpha sub V or beta, whatever you want to use, which is for volumetric coefficient. Then we're going to have times the original length, and finally the change in temperature. So part A, we're going to see what happens at minus 30 degrees. So at temperature equals to minus 30 Celsius, typically you want to work in international system. What happens is that Kelvin scale and Celsius scale both have the same steps. So when you make a difference in temperature, it doesn't matter if you work in Celsius or Kelvin, because going from Celsius to Kelvin is approximately, temperature in Kelvin is approximately temperature in Celsius minus 273 degrees. And so, or 273 degrees, I don't know, this is a good question. 273 degrees. So if I have something in degrees Celsius and I subtract 273, I find the temperature in Kelvin. Kelvin is an absolute scale, so it doesn't really have degrees. That's why, as we saw, so that's why the temperature when there's no kinetic energy, that's 0. That's an absolute reference. We don't need anymore to bring boiling water or cold water to say, or freezing point to say this is a reference point to describe a scale, and we make 100 points in between, as Celsius did for his centigrade scale. In this case, we're going to have an absolute number that corresponds to the average, or to something proportional to the average kinetic energy of the particles. But because this is the case, if you subtract this, you convert this temperature into Kelvin, and then you convert also this one into Kelvin. If you subtract it, you're going to have minus 273 minus 273, so you're going to have plus. So the conversion factor changes. This is not the case for Fahrenheit. You have to be careful in the case of Fahrenheit. So in the case of Fahrenheit, convert first to Kelvin and then make the subtractions. So let's calculate the temperature now. We're going to go to minus 30. So what's going to be the change in temperature? Is going to be final minus initial, as usually when we calculate an increment or a difference, and that's just simply going to be minus 30 minus 20, and that's minus 50 Celsius, or minus 50, now we can keep Kelvin, and we're all good, because it's going to be the same, minus 50 Kelvin or minus 50 Celsius. The difference in temperature, again, it doesn't matter, it's the same to use it in Kelvin or Celsius. Let's pretend this in Kelvin, because we always want to work in international system. So then the next thing we're going to have to find is what is the coefficient of expansion. And for the steel, we're going to find that alpha for steel is going to be 1210 to the minus 6 inverse Celsius. And this is degrees Celsius the other way. And this is another thing, 1210 to the minus 6 degrees Celsius is going to be the same if it's in degrees inverse Kelvin. Why? Because this is going to be multiplying this one. So it's the inverse of temperature. It doesn't, in this particular case, alpha is going to be the same. You don't have to convert it anywhere. There's no way to convert in this. This value is the same in Celsius and Kelvin. It's because of this that we were discussing. Anyway, so we just change the change in length. In this case, it's going to be 1210 to the minus 6 for alpha, the original length, which is 200 meters, that we can write as 10 to the 2, because 200 meters is 10 to the 2 meters. It's just in scientific notation. And then finally times 50 or minus 50 Kelvin. And if you make this number, it's going to be minus 12, 10 to the minus 2 meters. And so what is the change in length when it cools down? When it cools down, the thing shrinks because alpha is a positive number. If it was negative, it would be the opposite behavior, right? That would be an anomalous behavior of thermal expansion. But in this case, it increases. We can do the same thing, but now for the hot point. In that case, the hot one is going to be 40 degrees Celsius. And so the difference in temperature is going to be 40 minus 20, which is going to be 20 Celsius, or let's say 20 Kelvin, just to keep that the same as before. And so we can say that this is also the same as 1210 to the minus 6 inverse Kelvin. And so now we're going to find is the change in length, and we make the calculation is going to be the same, 1210 to the minus 6, and now times 200 times 20 Kelvin difference. And if we make these numbers, that's going to be 4810 to the minus 2 meters. And so we see that this one is negative, means it's compression. This is it's shrinking. This one is increasing. It's expanding. Why is this relevant? Because of course this is in 10 to the minus 2. We can put it in 10 to minus 3, and that will be like in millimeters. So this is 0.12 meters, right? So we could just say that this is 0.12 and this is 0.48 meters. Over 200, that's less than a half percent point. But that might not look like a lot, but that might be very important, because if you actually have it constrained, we will see in an example later, that's going to experience a force constraining that, or that tensile effort, or that compressive effort is going to be resulting in a thermal stress, and then you're going to have to see whether your material can sustain that sort of stress or not. It's the maximum stress, compressive or tensile stress that your material is going to sustain. And because these things can change, it might not be a lot, but overall an entire reach is going to be very important. That's why you see many times there's gaps and there's joints that allow for thermal expansion for these things not to be a problem. So these are calculations that engineers need to take into account when they're designing something, and this is just a classical example of thermal expansion as a result of a solid being expanded its thermal expansion, linear thermal expansion for the case of a solid. Potentially, we could imagine that, and that's actually going to be the case, the beam is going to be like a three-dimensional beam, right? So let's imagine it's just like a bar like this. And we can say, okay, it's expanding in this direction, but certainly it's going to also be expanding in this direction, it's going to be expanding in this direction. And those things are right, but typically when you have a cross-section or you have an object where one of the dimensions is significantly larger than the other ones, the only one that really matters is the one, because the change in length is proportional to the original length, the one that's going to have a much more relevant change in length is going to be the one that has the largest dimension. If you have objects, as we were discussing before, for instance, instead of being a beam, you had a plate, then the thickness will be negligible with respect to the length and width, right? So we could just make something like this and say, oh, if this was a plate, maybe it has a very thin thickness. Well, then this thing is going to expand in area. And typically for solids, when they're isotropic, this then will become twice the linear one, and we will account for the change in area as twice the change of the original area. That's how we can calculate for areas, or just initially just calculate the change in one dimension, the change in another one. That's another way of doing it. But basically, this is expansion for solids. Let's see an example for liquids. So we can see problem number 3 in discussions. In this case, we have a 70-liter tank of still, let's say there's a tank and there is some gasoline inside there, and the gasoline at 20 degrees Celsius, so that's going to be the original initial temperature, and it occupies a volume, which is again the original volume, of 70 liters. Okay, and the car sits in the sun, and the tank reaches a temperature of, the temperature changes to be now 40 degrees. And the question is, how much gasoline do you expect to overflow from the tank? So we have to imagine that this goes all the way up to the brim. So the gasoline is in there. If this expands, obviously we expect the liquid to expand and then start overflowing, because it's larger volume that actually fits the tank, and so the liquid is gonna fall, right? So what we're going to do is just basically calculate what's the change in volume. So we can calculate the change in volume, which is going to be now the coefficient of expansion, but now volumetric for gasoline, times the original volume times the change in temperature. What's the change in temperature in here? That's going to be 20 degrees, but let's start with the volumetric expansion coefficient for gasoline. For gasoline, volumetric expansion coefficient is going to be 950 10 to the minus 6, 50 10 to the minus 6 inverse Kelvin or inverse Celsius. And so what we're going to find is that if we write this thing here, this is 950 10 to the minus 6. Original volume is 70 liters. Now remember, let's make it just explicitly once more. The 1 liter, it's equal to 1 cubic decimeter. Now 1 decimeter, let's maybe make it in here. So let's make it in here. So let's say 1 decimeter. If you forget about how to go from decimeters to meters, always start from your reference point. If your reference point is 1 meter, then you know the 1 meter deci is going to take 10 decimeters. And because decimeter is small, one of these takes many of the small ones. And so you can invert that and say that 1 over 10 meters is 1 decimeter. Now the thing here is just to realize that we're not working with decimeters, but with decimeters cubed. So what we're going to have to do is to realize that we have 110 meters cubed is going to be equal to 1 cubic decimeter. So let's see if this is in frame. And that's going to be 1 cubic decimeter. So of course it's going to be 1,000th of, right? So that's going to be 1,000th of 10 to the minus 3 meters, cubic meters. That's what 1 decimeter is in cubic meters. What's important because of that, then we're going to know that 1 liter is actually 10 to the minus 3 cubic meters. Okay, so when we write this thing, we have 70. We don't have 70 liters. We have 70 liters. It's going to be 70, 10 to the minus 3 cubic meters. So we have to write it in cubic meters, 10 to the minus 3 cubic meters, and then times the change in temperature, which is just 20, because it's 40 minus 20 is 20. And so we make this calculation. We find that this is about 1.3 10 to the minus 3 meters cubed, which is equivalent to saying 1.3 liters. If you want to make it back, put it back from cubic meters to meters, 1,000 goes there. So 1,000 cancels, so 1.3 liters. So changing from 20 to 40 degrees under the sun, which is something actually pretty realistic in the sense because your car is going to get much hotter than that, you can increase at 1.3 liters the volume of gasoline. And of course, that's going to be the volume that overflows and falls out of the tank. There is a particularity in here that's interesting to notice, which is, okay, this is the change in volume for the gasoline. But the gasoline is not a steel tank. And so we would expect that, of course, gasoline is going to expand, but so is going to do the steel. So how much is the change in volume for the steel? So if we take the volume of a steel to be just even the same thing, the change in volume being the volume for a steel to be 70 liters itself, just for the sake of the experiment. So instead of imagining that you have a tank hollow, you have a solid tank. That would be the idea, right? We could change how much is the change in volume for a steel. And in that case, it's going to be the change in volume for a steel times, obviously, the original volume times the change in temperature. Change times the change in temperature. Now, we don't know the steel, but we know that the linear steel, we just said it, that was the linear coefficient in the previous problem. We said that that was 12, 10 to the minus 6. So in a first approximation, we can approximate and say that the volume expansion coefficient for a steel is going to be approximately 3 times that of the linear, and so take it as to be 36, 10 to the minus 6, right? Otherwise, just go to the tables and find the extra number, but this is a very good approximation. And so we're going to find that this is 36, 10 to the minus 6 times the original volume, which we said 70, 10 to the minus 3, and then the change in temperature is still the same. And so if you make these numbers, what you can find is that this is actually, I think it's 49 times 10 to the minus 6 cubic meters, which is anyway 49 10 to the minus 3 liters, or 0.049 liters. So what we observe from here is that the expansion of the same volume of steel compared as to gas, gas expands 1.3, which is above, it's probably 1.3% of the entire volume, right? Whereas in the case of, or 1.2% of this volume, right? Yeah, so that's the amount of volume that it expands. But how about the steel? Even if you were considering to be solid, that will expand only 0.049, which is like this is 1,000 times less. It's actually 10,000, about 10,000 times less expansion or 1,000 times less expansion than the gasoline. So the expansion of the steel tank is not enough to account for that. And so what's going to happen is, of course, the gasoline overflows. And so sometimes you might experience things like that if you fill the gas tank to the brims. It never happens usually because there's a safety pin about a safety sensor and everything to stop typically in the petrol station, in the gas station, to stop the gas from overflowing out. But what you're gonna observe is that if you fill it to the, let's say, maximum, you fill the tank and you park your car under the sun, sometimes you're gonna be smelling some smell of gasoline, and that's of course also related to the vapors. But the seal is supposed to be sealed. What happens sometimes as the car gets old, some of the O-rings or gaskets crack, so some of the fumes expand. So usually just don't overflow stuff. Basically, never take it too low. That's also a good idea to avoid issues with the pump and also avoiding the dust to fall into your injectors. But the idea here anyways is liquids, gases, we'll see gases now, but fluids and solids expand differently, and in fact they expand extraordinarily different, because there's like 1,000 times difference between the expansion of solids and the expansions of liquids. And if this is amazing for liquids, or let's say it's large for liquids, it's even more for gases, which is going to be the next example we're going to see. Let's solve problem number 6 from discussions. This is for a tire, and it says there's an automobile which right, and after driving for 100 kilometers, the number is just there. The gauge pressure of that is 210 kilopascals, right? So that's going to be 210 kilopascals. And this is the gauge. So remember the gauge pressure, that absolute pressure, excuse me, it's gauge pressure plus atmospheric pressure. And this is very important because whenever you use in PV the ideal gas equation, you have to use not the gauge pressure, which is this one over here, but the absolute one, okay? So very careful. They're telling you the gauge pressure, which is one that usually you're measuring in your car. And this is at 10 Celsius. But after driving for 100 kilometers, the temperature in the tires is 40 Celsius. And so the question is, what is the pressure within the tire now? Now, of course, it's going to be the pressure within the tire. And when we're working with gases, we know that the gases do not expand the same way. It's different. We're going to have nRT. Let's use this ideal gas equation. Number of moles, the ideal constant ideal of gases, and temperature in Kelvin, okay? And depending on how you use these units, you could use different units in here, atmospheres and liters, or just directly pascals and cubic meters. So use R to be in joules. Okay, so that depends on how you're working. Be careful for what value you use for what units. Are you using, once you choose that value, of course you have to choose these units accordingly. So the first thing we're going to see is we're going to realize that the number of amount of material inside the tire, of course, doesn't change from one scenario for another. So what we have is you can rewrite this thing as saying that the pressure times the volume divided by the temperature is going to be equal to N times R, and that's going to be constant, because we are not changing the amount of material as we're driving down the road. Typically, if there's no leak, that's not going to happen. So this is going to be what needs to be constant. And so we're going to have in the situation first, let's say cold. In cold, we're going to have pressure 1, V1 divided by T1, okay? And then we're going to wait and say warm. In warm, we're going to have P2, V2 divided by T2. We have T1, which is this one, or T sub 0. We have T2, which is 40 degrees. We can just write it here. T sub 2 is going to be 40 degrees. We have the initial pressure, and we want to know the final pressure, actually, P2. That's actually the question. And, of course, the problem here is that what do we know about the volumes? So, because we can consider the volume in the tire to be constant, that's going to be the assumption here to make it, because the tire is not really expanding much. You could calculate how much is going to be, because the thing here is that, yeah, the gas tends to expand, no question, but the tire is going to be made out of some sort of rubber, which is not going to expand as much because it's a solid. So as we just saw in the example of gasoline, typically when we have a solid and a liquid, in most scenarios, you're interested is how much does the liquid expand with respect to itself, because the solid does not really expand much. So we can make in a first approximation that the volume of the tire is not going to change, because the volume of the tire, which is the available space for the gas to move in, is given just simply by the rubber of the tire, right? So in that sense, we can take that V1 is going to be equal to V2, and it's going to be equal to V. We would have to count first how much is the expansion of the rubber of the tire, the volume of the tire, and what's the expansion here, for a given volume, how much it expands that. But this is in a first approximation going to be very precise, anyways, very precise approximation, because the increase in volume of that rubber as a solid is going to be very low. So then that's going to become easy, because we just can say that this is going to be P1 times V divided by T1 needs to be equal to P2 divided by T2 times V2, and this is V, so this and this is going to cancel. So basically we're going to find that P1 times T2 over T1 needs to be equal to P2, which is the pressure at 40 Celsius. Now, important, first of all, the pressure here needs to be absolute. So remember that P absolute is going to be 1 absolute is going to be our atmospheric pressure, which is 10 to the 5 pascals approx, plus the gauge pressure, which is going to be 210 kilopascals. So that's going to be 2.1 10 to the 5 sorry. Yeah, correct, that's 10 to 5 pascals, right? So that's going to be about 3.1 10 to the 5 pascals, which is the pressure that we have to introduce here. So we're going to put 3.1 10 to the 5, and then the temperature in Kelvin. So now we have to convert the temperature into Kelvin, and 40 Celsius, we have to add 273 Kelvin. Because 0 Kelvin is the lowest, so if you have a question, then it becomes so easy to realize, do I have to add or subtract? Well, you cannot subtract. If you subtract, it becomes negative, and there's no negative Kelvin. There's no negative temperature, right? Kelvin is absolute, so of course it's going to need to be an addition, and that's going to be 313 Kelvin, and there's going to be an addition here, which is 283 Kelvin. And now we can write those numbers and then make the product, the ratio 313 divided by 283. And that's going to give us the total pressure too, which is again absolute pressure, which is going to be 344 kilopascals. Now, importantly, the question is about what is the reading of your detector, your barometer, and that is going to be gauge pressure, not absolute pressure. So you know the absolute pressure, you have to convert it into gauge pressure, and so we know that P2 absolute, this is the absolute one, right? It's 344, but that needs to be P absolute minus P0 is going to be the P2 gauge, which is just basically subtracting 100 kilopascals to 344, right? Because P sub 0, which is atmospheric pressure, it's 100 kilopascals. We're taking it to be 100 kilopascals. So that's going to be 244, and that's actually what you kilopascals. Now we can compare the 244 to the 210 initial, so we have a 34 kilopascal increase, which is about a 16% increase in this value, just the result of driving for, let's say, 100 kilometers and increasing to 40 degrees Celsius. The pressure is going to increase. Because of this, typically, when you're measuring the gauge pressure of your tires, which is very recommended before, for instance, well, regularly anyways, but if you forget to do this regularly, at least do it a few times, and certainly whenever you're going to do like a long trip, and make sure that you measure the gauge, or you measure the pressure of your tires when they're cold. So they say do not drive for more than, typically they say like a 1 mile or a couple of kilometers, so before you measure, because if you drive for long, temperature is going to raise, so the actual value you're reading is not the value that the manufacturer is telling you. If you're reading the tire, it's going to have written usually in different units. For instance, this could be in PSI, right, in pounds per square inch, which is a measure of pressure as well. It's just pounds mass on square inch over an area, so it's a pressure. And I don't know, I think this is 35 psi. So this is 35 psi that you have, when in reality the value shouldn't have been 35 psi, it should have been, let's say, 16%, a little more than that, lower. So you are going to be thinking I have the right pressure, when indeed you may be already below the range, the recommended range, because you're measuring with a hot tire. So this is an interesting application of a phenomenon that now we can understand. Why does the manufacturer recommend you or tell you to actually measure? Because the references that they're giving you for the range of pressures is for a cold tire. If the tire gets hot, the gas inside gets hot, it's going to have a larger pressure, your readings are going to be off. Let's say a classical question, conceptual but also practical question that sometimes we just don't realize because we rush to conclusion and then we're wrong, which is the idea what happens when you expand a ring. So the idea was basically this way. If I have a disk, solid, and I increase the temperature, I expect this disk to increase in area, right? So this is what I expect when I increase the temperature. And so a classical question is just what happens if instead of having a disk, now I just say I have a ring, right? So now the solid area is just this one over here. What happens if I increase the temperature? So sometimes we feel that, yeah, maybe the thing just goes larger, but the inner diameter, let's say, it closes down because it's expanding. So it expands towards the outside and has free space in here, so it expands in that direction, right? But this is wrong. This does not happen. What happens actually is that what you obtain is a larger ring, certainly, but you have a larger inner diameter. So this is what happens in reality. Why do we think this way? is typically because we think that the expansion is happening in this direction. There's an easier way to see this. The ring is ultimately made out of, if you want to understand that, let's say there's a ring. You can say that the ring is made out of very small rings or very small diameter, like a collection of concentric rings, if you wish, and going forth, so forth, blah, blah. Okay, so if I just take a single one of those, which is going to be, let's say, like this, I could just cut it through here and stretch it, and what I expect to find is something like this, right? And I ask you, what do I expect to find if I say that there is heat happening here, or I subject this to thermal expansion? Well, what's going to happen is it's going to expand, and it's going to expand like this, right? And this is the discussion we had before. It certainly increases also in this dimension, so it expands also in this dimension, but in compare with the length, it's negligible. So what matters only is just the length. Now I take this, I make a ring again. What do I'm going to find? I'm just going to find this. So the thickness is approximately the same, but now the ring is bigger. So this size has, this inner ring has increased. And we're assuming, of course, that these are perfect circles, right? So this is the result of that. We're expanding linearly, and because it's pushing, it pushes towards the outside. It's not that it's expanding the thickness, which is indeed expanding, but that's negligible. It's actually expanding towards the outside. So if now you have this, and you have several of those, each one of those is going to happen this, so you're going to end up having that the inner one is going to expand, so the inner circle is going to be, or the whole of the ring is going to be larger, right? So this is just conceptually to see how we can combine everything to realize why rings do not contract, but actually expand. And problem number 2 is an application on this principle. Let's erase quickly here, and let's solve that problem. The question now they're asking us, it says that there is an iron ring that needs to fit snugly on a cylinder rod at 20 degrees Celsius. The diameter of the rod is, this is the rod, and then we need to put, let's say, a washer or a gasket or something, right? And this is the gasket that we need to fit in there. So the diameter of the rod is 6.445 centimeters. The inside diameter of the ring, it's because, of course, we don't care about the outside. I mean, in this particular problem at least. The inside of the ring, we just need to make sure that that fits in there. It's 6.42. So, of course, this is smaller than this. It doesn't fit. So here's the idea. Because it expands, why don't I just warm up this thing? It expands, it fits, and if it cools down, it's going to fit snugly. So that's the way of applying this thing, and so we expect, obviously, if it doesn't break, it's going to be fit there pretty much forever, right? So then, to slip over the rod, the ring must be slightly larger than the rod of diameter by actually 0.0. So let's say the target diameter, it's the rod diameter plus 0.008 centimeters, which of course that's the total of 6.53 centimeters. So we want to have a diameter that it's larger than, at least, right? Larger or equal than, let's say, let's make this larger or equal than 6.453 centimeters. To what temperature must be the ring be brought if its hole is to be large enough so it will slip over the rod? So again, this is the idea. We're trying to expand the entire thing. We're concerned only about that ring. And we're going to start saying what is the final temperature, which is another way of saying what is the change in temperature. And we're going to be using the idea that the change in length, it's equal to the change, linear change in original times the increase in temperature. So we can rewrite this thing by saying that this is delta of length over the original length, excuse me, times the change in, in the linear expansion, thermal expansion coefficient. Now you might be wondering, why are we allowed to use this equation? Why are we not just using the area, for instance? If you use the area and then you say this is about twice because it's a solid, isotropic, and so forth. But here's the thing, actually this is one line, as we said. If we take the ring and we stretch it, that's a line, and the line extends in length. So of course you could say that the length is not delta L as the diameter, the length is 2 pi, or in this case pi times the diameter, right? Because the length of the ring is going to be 2 pi r, the radius of the ring, but because the diameter is twice the radius, it's just basically pi times the diameter, correct? But if you put pi times diameter and you have pi diameter in here, what you're going to find is that there's going to be pi times diameter final minus pi times diameter original times divided by pi times diameter original. And so we can rewrite that as pi times 6.453 minus, I'm factoring out the pi, minus 6.42 divided by pi times 6.42, which is the pi's and pi's cancel, and this is 12 10 to the minus 6 because it's for Celsius. So if you make those numbers, you find that this is about approximately 430 degrees Celsius. The change in temperature needs to be 430 degrees Celsius. But there's an important thing here. This is the change in temperature, and the temperature was originally 20. So, and this needs to be larger than, that's what we were saying in here. So actually what you're going to find, the temperature at which you need to heat it is going to be 430 plus 20. It's going to be 430 plus 20, which is larger than 450 Celsius. So that is the final solution. What is the temperature we have to raise? Up to 450 Celsius. But now more important, we have seen a particular application. This, if you ever need to design a system and say it doesn't fit, you can warm it up, expand it, fall in there, and when as it closes, it's going to be fit snuggling, so it's going to stay there. The thing here, for instance, that we can just say is, this is, by the way, the expansion and contraction is sometimes why you use, it depends, but you should use like oil, penetrating oil or something. But you can use like a torch and then cold water to create some thermal shock. We'll see thermal stress in a second on a bolt. For instance, you're trying to fix your car and there's a bolt that's seized in there because maybe it's rusted, and then the rust generates the layer, and there's binding where you can warm it up and then close and cool it down to try to create some shock that breaks those bonds so you can loosen the bolt, right? But this is the same idea of thermal expansion and contraction. Now in this case, we're trying just to make it snug, so we have to expand it, it falls, when it cools down, it's going to go back, and it's going to be just fitting properly in the rod. Important thing here, don't make that mistake. Don't say the ring expands this way. The ring does not close its inner diameter. It always increases the inner diameter. And if this is kind of counterintuitive, it's because we expect this to be expanding in both directions, but that's not what we're interested in. Everything is expanding mostly. It's going to be negligible in this direction. Mostly it's expanding in the longitudinal direction. And that's taking a smaller portion of a ring, extending it. It goes like that. Let's roll it back. We have a larger ring. And it's, in that sense, it's going towards the inside because of the thickness, but that's negligible, again, with respect to the other one. And it's so large that, yeah, you go, let's say, much larger than you actually, it goes towards the inside with the thickness, right? And this is the same idea, basically, but now you have entire things being solid, so they just don't that small thickness increase, which is actually taking care of filling the gaps, if you wish, right? But important thing, it's a classical misconception. Rings do not expand by closing the inner diameter. They do not. And now we see a way of understanding, oh, if it's linear expansion, because I can take the ring, expand it, expands, I fold it back, I have the larger ring. Let's see now one example on thermal stress. We just said if there's an object that's subjected to some temperature, it just expands, a solid, let's say. But what happens if that thing is constrained not to expand? What arises inside the material is a result of the reason why it doesn't expand, as it will freely, right? Let's say let's have a material and I subject it to some temperature change, so it expands, and we can just make it even if we want. It expands like this, right? And I say, but now if it was constrained, or let's put it down here, if it was constrained, now what I will find is that this thing goes like this, and there's a change in temperature. And now there's a change in temperature if this thing is constrained. When there is a change in temperature, the bar is going to be the same length because it cannot expand. Why is the same length when I know it would expand? Because there's a force keeping it in place, and the result of that force is a thermal stress. Because of the expansion didn't happen, we have thermal stress. There's no thermal stress in here, there is thermal stress in here, okay? And so This problem in particular is just an application of that phenomena, which is historically relevant, and it's still relevant today because it's for engineering and the care. Why we have to be careful when designing this thing, which is the case of a steel railroad track that has a length of 30 kilometers when the temperature is 0 Celsius. Yeah, that would be amazing. 0 Celsius. Okay, so at 0 Celsius is 330 kilometers, right? What is the length on a hot day when the temperature is? What is the length on a hot day when the temperature is 40 Celsius? Suppose the track is nailed down so that it can't expand. This is the critical part. Now we're not gonna have expansion when it's nailed down, right? So, and once it's nailed down, what stress results in track due to the temperature change? And they're telling us that the expansion coefficient, that now it has changed, but basically it's going to be still, so we can take it 12. But let's be consistent with our previous cases, right? And so we're going to analyze two cases. Let's say it's free expansion. If it's free, what's going to happen? Well, the change in length is going to be equal to the linear times the original length times change in temperature. What's the original? That's 12 10 to the minus 6. What is the original length? That's 30,000 meters. What's the change in temperature? That's 40 minus 0, that's 40. And so we can just calculate this much. So if we make these numbers, this is about 14 meters. So what's the expansion over 30 kilometers? Is only 14 meters, but now it's not anymore only, because 14 meters is quite a stretch, right? So it's quite a large expansion. So that means that if you actually have the things bolted down or clamped in so they cannot expand, what's going to happen is going to start having a lot of stress avoiding this. Typically, you wouldn't build like an entire, you cannot pretty much fabricate an entire beam of 30 kilometers long, right? That would be technologically almost impossible. That you have to make the joints to be able to have some room for expansion because of this, because now we're going to distribute these 40 meters on all the kilometers, right? So, because you're having about half a meter every kilometer of expansion, right? We can just bring these numbers. It's about half, so it's half a meter every kilometer of expansion. So think about how much that is and how impactful that's going to be. Now the next question they're asking us is then what is the stress which would arise as a result of having the beams constrained, right? The question says, by the way, this is problem number 7, not 8. It says what stress results in the track due to the temperature change. So what's going to be the definition of stress? Well, thermal stress is the same as any stress is Young's modulus strain. Now what's going to be thermal strain? It's going to be the change in length due to the temperature. And what's going to be the Young's modulus of steel? We have to figure that one. Young's modulus is 0.2, well, it's going to be Young's modulus for steel. It's going to be 210 to the 11 pascals. So now we can just find that the thermal stress is going to be the result of that force preventing this expansion happening, right? And so it's going to be 210 to the 11 times 14 divided by 13,000, or 13 times to the 3, which is going to be approximately 9.3 10 to the 7 pascals. So this is a lot of stress, and this obviously 30 kilometers, we could just see how much per meter or something. And then you have to see whether this stress is going to be, well, that's actually stress. This is what it is. Not per kilometer, it's a stress. Excuse me. So we see that that's 9.3 10 to the 7, so it's going to be 93 megapascals of compressive stress. To go to steel and see how much is this is 93 megapascals, right? And what we have to see then is whether this stress is too large steel to sustain it, or if steel will break. So if you go to the Wikipedia or any other handbook, you might find a table with some typical values for the maximum compressive stress. In the case, for instance, of steel, it's 250 to even 1,000 megapascals, so that's safe, that's what you use steel. But if you check with other materials, such as, for instance, the adult bones is like 130, so we would be still okay for female being a little bit lower than for male. That's also related to density. But for concrete, for instance, that's 70 meters. So we would not be able to make a beam 70 meters. We could actually, 30 kilometers, but long, right? If we had we wanted to use concrete, because the stress would be too much and so it would break. Now this is going to be a lot of stress. The material is going to sustain it, so it might be fine. Now, of course, the question then becomes a little more particular, which is whether the thing has been installed properly, whether there's any impurities in the steel, and many other things that the engineers would have to take care of. But as a conceptual idea, we understand why there is thermal stress occurring, because there is a force which is the constraining force that prevents the thermal expansion that would happen in the free space. If you want to calculate how much that is, you're going to have to first calculate how much would expand freely, and then introduce it in the equation for thermal stress using the Young's modulus of the material. So materials more elastic than others are going to be playing a role in there. And from that we can just calculate what's the thermal stress, and compared to the maximum compressive stress in this case, could be tensile, in this case it's compressive. If, for instance, if we're saying what happens when it's 40 degrees, what happens when it's winter and it's, if let's say it's Alaska or something, it's minus 20 Celsius outside or something crazy like that, right? So there's going to be a tensile stress, because the thing is going to try to, the bar is going to try to compress. We could just take minus 40 degrees just to make it symmetric, and then instead of expanding 40, it will be compressing 40 meters. Then strain is going to become negative in that case, right? And so it's going to be minus 93, and then it's going to be negative, so it's going to be tensile stress, because what's happening is that these clamps are pulling from the steel beam trying or preventing that thing to shrink in size. So basically this is just the idea. We saw in the chapter of solids what happens when you apply forces, shear, which is the deformation of shape, and normal stress, which is the deformation in size. There's sort of a normal stress because it's a force opposite to that expansion, but it's not a result of, or is the result, let's say, of an object being constrained and trying to naturally expand. There's no thermal stress when you're in free expansion. That's the definition, because there's nothing constraining. There's no external forces. The external force is not the force of the atoms, it's the force of whatever is holding it in place. Important subtlety here to understand why do we have stress, but we don't have any stress in here. Let's see just one more example on thermal expansion, but this case for gases. In problem number 8 in discussions, we have an interesting scenario. We have a bottle that contains a message. Let's say, right, and it has some message here. The message is irrelevant, but there's a cork in the bottle. And so we say, the wording says that the beachcomber finds it, so very exciting adventure, I guess. The air in the bottle is at atmospheric pressure. So the pressure inside the bottle is atmospheric pressure, basically. That makes sense, because whenever they prepared the bottle, they were in planet Earth, and planet Earth, atmospheric pressure, we can take it, let's say, at least if they threw it to the sea, to the water, is presumably because they wrote it by the beach, right? So the pressure is going to be the pressure, atmospheric pressure, because we take it with respect to sea level, which is where they were, right? So it's a very good guess to say it's inside going to be at atmospheric pressure, if there's no leaks and this and that, anyways, yeah. And then this was built, let's say, or this was prepared at a temperature of 30 Celsius. Now, of course, why would you know that? You wouldn't, but we can assume that it was written one of those sunny days by the beach, and the guy wrote that thing, put it there, threw it to the sea, comes back to the beach or another beach. We have that scenario. Okay. We could use actually this the reverse. You could think of a problem where you try to figure out what was the temperature when they originally put this atmospheric pressure, based on the fact that it was from all the things we're going to see later anyways, right? But what we were saying over here is that the cross section, by the way, of that is 2.30 square centimeters. Going from square centimeters to square meters. That's going to be 2.3, and then meters is going to be 10 to the minus 2 squared meters. Okay, so it's going to be 2.3, 10 to the minus 4 square meters. Okay, because it's 100 times dividing for meters to centimeters, but we have centimeters squared, so it's 100 times squared, right? 10 to the minus 4. Very good. And the question is, at the temperature of 99 Celsius, so maybe the guy just put it in, it says in the fire, but you could just put boiling water and submerge it in there, and what you see is that the cork gets ejected from the bottle. And this is what is the pressure in the bottle just before the cork left. So basically, what's the pressure? It's building pressure to the point that it's too much, and the thing just escapes. What's the pressure at this temperature? Okay, what is this? This is a gas. We can assume, or we're gonna make the assumption that it behaves like an ideal gas. And so we're gonna have the classical equation that PV is equal to nRT. And now, of course, we know that the amount of material is the same and the volume of the bottle is the same because we're taking the glass. We've seen that. Solids do not expand mass as gases, so we can disregard the expansion of the bottle. And then you say that P divided by T needs to be the same as nRV, but this is constant. So then we have Charles' law, as before, this is constant. Okay, and so we're going to find is that at the beginning we had pressure initial at the temperature initial, and that needs to be the same as the pressure final, at the temperature final. What was the pressure initial? The pressure initial was atmosphere. We're going to take that to be absolute value, and so we're going to have the absolute value to be atmosphere, so that's going to be 10 to the 5 divided by the temperature initial, which is 230 plus 273, that's going to be 303 Kelvin, 303 Kelvin. That needs to be times, T2, that's going to be the pressure 2. And what's the T2? Right, so we're going to do this P1, T1 times T2, it's equal to P2. And so what's the T2? The temperature at the end, that's 99 plus 273, which is going to be 372 Kelvin. And so that's going to be here, 372. So if we just make those numbers, we're going to find that this is about 1.24 10 to the 5 pascals. So the gauge pressure being the difference between this and that, which of course is 0.24. Okay, so 24 kilopascals. Okay, the next question that says, what is the force that the cork would experience? What force of friction held the cork in place, right? So now we want to know exactly what happens to the cork. We of course need to make a free body diagram. So in a free body diagram, we have to consider all the forces acting on the cork. There's certainly a force pushing it outwards, which is going to be the pressure of the bottle, so we can call that the pressure. But why is that thing not leaving? It's certainly because there is a friction force holding it into place, right? Which is the question they're asking here. Now, is that all the story? Well, you might be tempted to say yes, but this bottle is not in a vacuum. This bottle is on Earth. The reason why this inside was considered to be atmosphere is the same reason why outside we have atmospheric pressure, because there's a column of air, which is atmosphere, pushing down onto the cork. So I actually have to account for an extra force, which is going to be the force of the pressure of atmosphere. So it's going to be, let's say, force of atmosphere. This is very important, because now when I make the balance of forces, an instant just before that, it's in equilibrium, so positive force is going to be force resulting of pressure 2, minus the force resulting from atmospheric pressure, minus the force of friction, and that's what's equal to 0. In other words, the friction force is going to be the difference of F2 minus F divided due to atmospheric pressure. This is the force due to atmospheric pressure, right? Because atmospheric pressure is also holding the cap in there. So that it's equal to friction, and the force into it's 124. Yeah. Times the area. So what we can do here, let's do this. What we can do here is realize that both forces act up on the same, or the result of pressures acting on the same area. So we can just write this as P2 minus P sub 0 times the area, which is the area. And then that's going to be the same as the P2, which is 124 10 to the 5 minus 1 10 to the 5, which is atmospheric pressure, times 2.3 10 to the minus 4. If you make the numbers, you will find that the force of friction holding it into place, that's going to be 0.24, and that's going to be about 0.40, something like that, so 4 point something, no? 5.29 newtons, let's say. So if you make the numbers anyways, you'll find 5.29 newtons. So it's a very interesting case. The question you could ask yourself is, what would have been the temperature required to achieve this? For instance, if you were in outer space. Well, if you were in outer space, this force disappears because there's no atmosphere. So now it's just basically a matter of balance. So it would take much less temperature because you will require much lower pressure, right? So anyway, that's just the idea. Typically, we just don't heat up stuff. We just use a corkscrew just to take it out. But it's a nice application of this principle. That also explains you take, for instance, a can of a soda or something. If you remove the pressure from the outside, now you don't have any more to balance, so that thing can explode because of the internal pressure of the carbonic acid inside, the carbonic gas inside, right? Or for instance, what would happen if you have a can of soda and you start warming up? Because you warm it up, the pressure is going to increase, and you have a different balance of pressure from the outside. It's going to start bulging, eventually it can just explode, right? So this is just ideas that we can see in here, basically relating pressure, volume, and temperature for gases. Let's see just one last example. We've seen it for solids, for liquids, and for gases. Let's see also one final example, which is something that we discussed during kinetic theory of gases but never demonstrated, which is the idea that never consider the fact that there is also gravitational force acting on the molecules. But why do we disregard it? Let's see why. So in problem 10, we're going to figure out why we were allowed to, or why we were okay taking the case that there is no other force or there's no other interaction between the particles that are called elastic collisions. Because certainly particles are on Earth, and Earth, it's always exerting this gravitational force on any mass, right? And so that's going to produce a gravitational force. Now, of course, if you don't change much of the height, then you could take, okay, it's fine. But if you have a large container, what about in that case, right? And so in this case, for instance, we're taking the container to be 1 meter. We're going to see that this is actually as large as you want within limit, of course. There's other problems that are going to appear before we actually start to consider effects of gravitational force in any case. So the question is, okay, down here the particle has no potential energy, gravitational energy, right? But up here is going to have a potential gravitational energy, which is going to be the mass GH. So are we allowed, are we okay, are we justified in regarding that contribution? There's a good way of assessing this, which is basically calculating the ratio of one to the other. Kinetic average energy of a particle is going to be given by 3/2 of Boltzmann constant times the temperature. Now in this particular example, we're being told that this happens at room temperature. So this, we're going to take room temperature to be 23 Celsius. So it's going to be about 296 Kelvin. And let's take the molecule to be oxygen. Now oxygen in particular is a diatomic gas, so it has 2 atoms per molecule. So each one of the molecules of oxygen is going to be 16. So we're going to have 32 of mass, right? So we're going to just be able to write the potential gravitational force 32 times 10 times the height, which is 1 meter. And so it's going to be 3/2 of kb times the temperature, which is 296. So if we make the ratio of the two, so let's write in here first that kb is 132 10 to the minus 23 joules per Kelvin. Let's make sure. 10 to the minus 38, but it's okay. Joules per Kelvin. And then the other thing we need to know is that, oh yeah, so if we take a molecule of oxygen, let's build it, right? So we have an oxygen here, we have an oxygen atom linked to another oxygen, right? These two are oxygen, so actually have 2 times oxygen to actually have O2, right? Each one of those oxygens has in the nucleus 6 protons, that's what defines oxygen, 8, which means that it's going to have 16 atomic weight, so units of atomic mass, right? So it's going to be 8 protons and 8 neutrons, 8 protons and 8 neutrons, in total 32 AMU or U. I don't know what you call this, which basically is the same as saying 32 times, and in this case the weight of a proton is 1 point, sorry for that. That was a surprise to everyone. It's gonna be, I think this is 167, 10 to the minus 24 kilograms. So if we put everything together, make the ratio, we can calculate that 3/2 of 138 10 to the minus 23 times 296 and divide by, oh yeah, this is missing. So potential energy is going to be mass, but mass, let's rewrite this. The mass of a molecule is going to be the molecular weight times 2, or the molecular weight of oxygen basically, right? And the molecular weight of oxygen is going to be 32 times U. In that case, it's going to be 32 times U times G times H being 1 meter, which is 32 U, well, this is 1 meter. So it's going to be 32 times 167 minus 24 kilograms per proton times 10 times 1. And if you make these numbers, you can obtain something of the order of 8.5 10 to the minus 5. So what is the corrective factor? So this is about slightly less than a millionth, well, slightly, no, a little more, but basically than a millionth of the kinetic energy. So the correction to, if you were to account for potential elastic gravitation of the kinetic energy, of the total energy of this particle, consider potential elastic energy, gravitational potential energy, is going to be of 1 part in 100,000th, if you want. So it's such a negligible, so it's going to be, if I have a number which is 3, I'm talking about 1, 2, 3, 4, 5. This is the sort of correction we're making in here, okay? So that's, it will be 1 more or something like that, but anyway. So that is the kind of correction we're talking. It doesn't make sense. We can just disregard that. It makes everything complicated, and our approximation is justified. This is just an application of this idea. Temperature is just the measurement of the average kinetic energy of the particles. In the case of oxygen, however, it's important to realize that oxygen, being a diatomic atom, is not just going to be simply translating around, and so this kinetic energy is not just going to be simply translational. It also needs to account for vibrational, where the center of mass, as we will see in the next chapter, doesn't change. That's what we define typically as vibration, and also rotational. The molecule can just be rotating, so it just can move around the entire thing. It can vibrate and it can rotate. So all those things have components of kinetic energy. The average kinetic energy needs to count for everything. But anyway, this first idea, or this idea, excuse me, of why were we justified on making this assumption, we now see it mathematically. This back of the envelope, so to speak, calculations are good to actually see that some of the assumptions that we make as we go make sense, and we're good. And with this, just to finish the chapter or the problems on temperature.